list of resonance structures with very similar mechanism grows and grows. We've changed one atom for another atom. We've even changed one bond for another bond, namely in the azide case, when instead of having a double bond to start with, we had a triple bond. Now we're going to look at an example where carbon is the first atom, nitrogen is the second atom, and oxygen is the third atom. Here it is. And given that we're fitting it to the same model, as you'd expect, we see the same mechanism. There is an extra oxygen with a negative charge on it, but it doesn't participate in the mechanism. Here's an example where we start with the arrow on a lone pair that is neutral. In this case, it's on an oxygen atom. The arrow ends in the middle of the bond between the oxygen and a positive carbon. Initially, it doesn't look anything like our first example, but let's think a little more closely. Look at the two arrows. Yeah, you can see it. They are very similar. In the first case, we have the arrow starting on a negative charge. But remember, that's still a lone pair that it's partly representing. And in the second case, it's starting on a lone pair of a neutral atom that is oxygen. But the arrow is the same. We've been looking at electrons moving in pairs, two electrons. We've represented this with the arrow having a double barb. Now we're going to think about moving one electron. Here's a molecule. You'll notice there is a dot on the molecule. This represents the one electron. It's called a radical. Now we can move that radical by drawing an arrow with one barb on it to show the movement of one electron. And if the arrow ends in the middle of the bond, you can see we're trying to make a double bond. But we know to go from a single bond to a double bond involves two electrons. So where does the other electron come from? Well, we have an adjacent double bond. We break that double bond. One of the electrons we use to create a new double bond. The other electron will end on the carbon, and that will be the site of the new radical. This is very different from moving two electrons. We've said that in general arrows go from left to right or from right to left, but always in the same direction. This is the big exception. Notice that here we do have arrows going in opposite directions. We also have arrows coming together. In the second step, we see the same process occurring, just moved down the molecule a little bit. This is also a resonance structure. We've talked quite a lot about resonance structure now. We know that more resonance structures makes for a more stable molecule, that the resonance structures aren't really real. They are an extreme of the molecule that it never actually will be. Resonance structures can change direction. They can either go forward from left to right, or they can go backward from right to left, and that's represented by the double arrow. The arrow movement can be the same. We can change the atoms and we can change the bond, but we are looking to make our lives a bit simpler. So it's always good to look at the arrows and see if you're recognizing any patterns that you might have seen before.